Hi everybody, and welcome to the video on section 15.1. In this video we start an introduction to chapter 15, and chapter 15 is essentially a continuation of chapter 14 in the sense that chapters 14, 15, and 16 are all about statistics and probability. So getting you comfortable with the language of statistics and how statistics are presented. So in this video here on section 15.1, the section is just going to introduce you to several different kinds of visual representations of data. So graphs and charts will visually represent data for you. So let's start this section with a definition. A data set is a collection of data values. So you can call the values in the data set data values or data points. It doesn't matter. And for us in this chapter, we'll work with data sets in which each individual data point is a number. But in more complicated settings, you could have a data point be a list of numbers. But for us, a single data point is just a single number. Capital N, just like in chapter 14, is going to represent the size of the population. In this context now, the population is just the data set. And a real-life applications data set can range in size from small to maybe a dozen or so, to extremely large, hundreds of millions. The larger the data set is, the more necessary it is to have a good way to describe and summarize it. So suppose you have a data set that only consists of 12 numbers or 10 numbers, right? You don't really need a chart or a graph to show you what that data set looks like because it's small enough that you can visualize it yourself. But imagine a data set with hundreds of millions of numbers in it. If you want to now get a hold of what that data set looks like, one way you could do that is to open the Excel file, right, and just look at a spreadsheet that has hundreds of millions of lines in it. But that is not terribly practical. You will not get a good sense of what the data set looks like from just dealing with the raw data. So the bigger the data set is, the more necessary it is to have some sort of visual tool that removes you from the raw data and just sort of summarizes the data visually. So here's an example. In this example, this professor in his Stats 101 course has 75 students, and each data point inside the data set will represent a score that a student got on an exam. And so each data point is a score between 0 and 25. So that blah, blah. Okay, so here it just is the data. Okay, so there are 75 data points inside of this table, and each score is, oops. Okay, so each score has a student ID number with it. So if you just look at this table, 75 numbers isn't really that big, I suppose. But even just looking at this table, it's kind of a jumble of numbers, right? It's sort of hard to tell from this table how the students did, right? Like, how did the typical student do? How did the average student do? Did this class do well or not well on this exam? You know, questions like this, it's kind of hard to tell just from the table what has happened. So here you go. Like students everywhere, students in this course want to know, how did I do? So you can look at the table directly and get your score, but when a student asks, how did I do, what they really mean is, how did I do relative to the rest of the class, right? So what the student is really after is, how did the class as a whole do, and how did I do in reference to that? So to answer that last question, you could, of course, just like look at the raw numbers and sort of analyze, okay, so I got a 10. Well, that's worse than a 13, but it's better than that person's 9, better than that person's 7, etc. But it'd be nice if you just had a picture of this so you can sort of place your 10 visually inside of that picture. Okay, so in other words, what we need is a way to package the results into a compact, organized, and intelligible whole. And we're going to do that with a graph or a chart. So the first such chart that can summarize the data for you is called a frequency table. And so what this does is it has the data points across the top, and then it tells you how many times those data points appear in the second row. So what this says is that somebody got a score of 1 and one person got that score. Somebody got a score of 6 and one person got that score. Somebody got a score of 7, 2 people got a 7. 6 people got an 8. 10 people got a 9. 16 people got a 10, etc. Nobody got a 17. Nobody got an 18. One person got a 24. Okay, so the number across the top is a potential score, and the number down below is how many people got that score. So that's what a frequency table is. Okay, yeah, so as this says, you can easily see from the table that one person got a 6, 10 people got a 9, etc. So if you got a 10 on this quiz, then you're right here, right? And 15 other people got 10. So you sort of clustered there with a bunch of other people. So I suppose that's comforting, right? If you got a 10, from this little compact table here, you can see, oh, 15 other people got 10s also. And if you're comfortable with this word, 10 was the mode. So 10 occurred most often. So if you got a 10, you got the score that occurred most often. Okay, so a frequency table sort of summarizes the data for you in a better way than just the raw numbers do. But really the way that people usually summarize these data is they take a frequency table, so they take this table and they turn it into a bar graph. So like so. So in this bar graph, the scores are across the bottom and then the frequencies are the values on the vertical axis. And so 9 people got a score of 10, 10 people got a score of 16, etc. So if you compare and contrast this figure to this frequency table, what happened was these scores are across the bottom, they're on the horizontal axis, and then you just build a bar that has the corresponding frequency height. So you build a bar at 10 that has height 16, a bar at 14 that has height 5, etc. So right, a bar at 14 that has height 5, bar at 15 that has height 2, etc. So this now gives you a nice compact little handy way of seeing what the exam was like. You can immediately see from this that, oh, one dude got a 24, so one person did really well. One person got a 1, so one person did very poorly. Most people got between like a 9 and a 12, right? You can just immediately see that from a picture like this. And again, in this table here, here's the original raw data. You might be able to make these observations fairly quickly from this table because this table is not terribly big. I mean, it's not small, but it's not super big. But imagine that you were analyzing, let's say, ACT scores. If you wanted to analyze the raw data, then suddenly now this table is humongous. You have thousands of data points in a table like that, and staring at the raw data won't tell you much. But if suddenly you have a picture like this, you can start seeing patterns, right? You can start really seeing how people did. Okay, so as it says, bar graphs are easy to read. They are a nice way to present a good general picture of the data. Okay, a bar graph gives you sort of a holistic picture of the data immediately without having to stare at the raw numbers. So with a bar graph, it's easy to detect outliers, right? That's what we did on this previous slide. There's this one dude by himself over here, another guy by himself over here, right? You can immediately see that from a bar graph, and maybe you couldn't see it immediately from just the raw data. Yeah, so as it says, there are two obvious outliers, the 24, right, the curve-breaking guy that everybody else hates, and the guy who got a 1, right, who did worse than everybody else. Okay, so sometimes it's convenient to express bar graphs in terms of percentages, which is what your book means when they say relative frequencies. So the frequency is given in terms of percentages of the total population. Okay, so in other words, I'll show you a picture in a second, but here was the original bar graph. Sometimes rather than writing just a raw frequency over here, like 10 people got a score of a 16, I'm sorry, I said that backwards. 16 people got a score of 10. Rather than having a 16 right here, we would have 16 divided by 75 right here. So we would convert this number to a percentage. Okay, so that's what this looks like. Percentage of students receiving a score, 21 or so, right? 21.5% of students got a 10. 8% of students got an 8. It looks like about 1.5% of students got a 1, etc. So a lot of times you will see percentages on the left rather than the raw frequencies because with percentages there's a definite cap. You know, it goes from 0% to 100%. So this vertical axis here will never go past 100. But if you have a humongous data set, you can imagine that the vertical axis might run from 0 to a couple thousand. You know, if you're measuring income for example, there are several thousand people who maybe make 60 grand a year. So you'd have a chart that went from 0 up to 2 grand, counting by 2s or 5s or whatever. It would just be a humongous chart. But with percentages, you now have a definite cap on how high your chart goes, right? 100% is the cap. So this bar graph here, this relative frequency bar graph, and this one here are telling you the same thing. It's just that these raw frequency numbers have been converted to percentages. So now, right, 10, the bar of 10 used to reach up to 16, but now it reaches up to 21.5 because 21.5% of all the students got a score of 10. Okay, so here are two things you should be comfortable with. Bar graphs with just a frequency and bar graphs with a relative frequency or a percentage. Okay, so it's worth noting that from a relative frequency bar graph, you can get the original data back so long as at the top they tell you how many students there were. So if I removed this n equals 75 right here, you actually wouldn't be able to recover the original data. Okay, you can't recover the original data simply from a percentage. But if I tell you, oh, and by the way, there were 75 people, then you can figure out what 21.5% of 75 is. You can figure out what 8% of 75 is. And that's what the height on the original bar graph would be. So as it says here, figure 14.2 indicates that 12% of the 75 students scored a 12. Right? So here's 12, and the bar has height 12. So 12% got a 12. So if you take 12% of 75, that's 9. So you can actually recover the raw data back, and you can now figure out that 9 students got a 75. So here's one last thing to note about this. If you convert from frequencies to relative frequencies, or vice versa, you don't change the shape of the graph. It's just a change in scale. So this guy right here is sort of hump shaped, right? Builds up to a peak and then tapers off. That has the same exact shape as this graph, right? Where you had just the raw frequency. Okay. The next kind of chart I want to show you is called a pictogram. And the point of a pictogram is that a graph is often used not only to inform, but also to make an impression, like to impress or persuade. And a well-chosen icon or picture can be a more effective tool than just a bar. So it's essentially just, I suppose, an emotional effect is what you're going for. So the next slide is going to show you a pictogram of the exact same data we've been looking at. And it looks like this. Okay, so you got this dude down here who's really unhappy, right? You got this guy up here who's really happy. And then these guys are sort of like on the boundary between unhappy and happy. These guys are pretty happy. These guys are happy but less so, etc. So this sort of chart gives you the same data, but it gives you sort of an emotional assignment to each data point, right? This is unhappy, it's bad. But this guy over here is happy, he's good. Okay, here's another pictogram. It shows the yearly sales of some corporation between 2001 and 2006. And it's a good picture to show at shareholders meetings, right? But so instead of having a bar, you have a stack of cash. Right, so that's also a pictogram. Rather than using a bar, it's sort of more visually impressive to show stacks of cash. Right, it makes more of an impression. One thing it's worth pointing out, though, is that many charts, even though they're not lying to you, okay, this chart right here is not lying to you, it's actually quite misleading. So one thing you should always worry about when people give you charts rather than raw data. Okay, so a chart is sort of a summary of the raw data. It can be manipulated in all sorts of ways. So when somebody gives you a chart, you should always ask yourself, is this person trying to manipulate the way this is presented to me to make a point? And so in this picture here, notice that this bar over here, this 2006 bar, it's like 6 times as tall as this bar right here. And the 2002 bar is about double the height. Right, so it looks like a really impressive climb from 2001 all the way up till 2006. Right, it looks like you've essentially sextupled your profits over the 6 years or over the 5 years. But notice that this actually is not the case, right? In 2001, you made about 53 million or so, and in 2002, you made about 56 million. So you certainly did not double your revenue, or whatever this is measuring, right? Your profit from 2001 to 2002. You certainly grew, right? You grew by about 2 or 3 million, but you did not double your profit, right? And notice that from 2001 to 2006, you increased from 53 up to about 77. Okay, so that's not an increase of 6 times, right? It's not an increase of a factor of 6. You did not take the profits here and multiply them by 6 to get the height over here. So this graph is misleading. So something to worry about when people give you data, if they don't start the vertical axis at 0, it can be misleading as to what's going on. So here's a chart where I start the vertical axis at 0 and then go by tens, and notice you see the same growth, right? This is the same data, but this last bar now is no longer 6 times the height of the first bar. And this second bar is no longer double the height of the first bar. Okay, so something to worry about, again, when people give you visual data, even without directly lying to you, they can mislead you, okay? This chart right here, nobody was lying about anything, and yet they were still able to mislead you about the performance of this company over the last 6 years. This chart is more representative of what happened, right? You have a climb, but it's not this miraculous increase by a factor of 6 climb. Okay. So, in other words, the difference between the two pictograms can be attributed to a couple of standard tricks in the manipulation trade, stretching the scale of the vertical axis and cheating on the choice of the starting value on the vertical axis. So rather than starting at 0, the first pictogram started at, say, 55. So as an educated consumer, you should always be on the lookout for these tricks. You will see this kind of trick all the time if you look for it. So in graphical descriptions of data, a fine line separates, doing a good job of presenting the data and, let's say, propaganda of misleading, even without lying. Okay, so now let's move on to categorical variables and pie charts. So variables can describe non-numerical characteristics of a population sometimes. You can have a variable that measures gender or ethnicity, hair color, your feelings, and so on. These 4 examples here, none of them are numerical. Okay, gender is either male or female, right? Ethnicity is, say, white, black, Hispanic, whatever, right? These are all non-numerical things. So these guys are called categorical or quantitative variables. So categorical simply means non-numeric. And if you want to display categorical data, you can use a bar graph, but another nice way to do it is with a pie chart. So this guy here, this example here shows different majors, I suppose. So 22.33% of students at this particular school are majoring in a humanities major. And notice major is not numeric, right? You're a math major or you're a physics major, you're a whatever English major. Those are non-numeric variables. Okay, so a pie chart just shows you percentages of what percentage of people live in a certain variable, right? What percentage of people are of a particular ethnicity or have a particular hair color or whatever. Okay, so this is our last example for this section. The last kind of chart I want to show you is called a histogram. And essentially, this is SAT data right here. So it's 1.5 million or so students took the SAT. This is the score on the SAT, either math or English section. I don't remember which. But anyway, the scores range from 200 to 800. And so you can kind of see how the students did, right? There's sort of a peak right in the middle, right around 400. But notice now that the horizontal axis is not divided into individual numbers as it was before. So before, we would go from 200 to 201 to 202, 203, etc. But notice, if you want to have a chart where the horizontal axis stretches from 200 to 800, that's a lot of individual data points you'd have on your horizontal axis. So this chart would be humongous. So rather than having individual numbers on the horizontal axis, in a histogram you condense into, I call them bins. So you cluster them into ranges of data or intervals of data. So this first interval is from 200 to 249. The next interval is from 250 to 299, etc. And so what this is saying is that slightly more than 200,000 people got between a 400 and a 449, for example. Slightly more than 50,000 people got between a 700 and a 749, and so on. So a histogram like this shows you the data in an aggregate way. And so notice now you've completely lost the original data set. So since you've condensed this 350 to 399 into a single bar, it's possible that all 125,000 of these people got a 370. But it's also possible that half of them got a 350 and half of them got a 380. You just don't know. All you know is that 125,000 people got between a 350 and a 399. So when you start aggregating like this into intervals, you lose the original data set. Okay, so when numerical data is continuous and in small increments with no gaps, histograms are a better way to display the data. And so in this particular case here, the only difference between this picture and this picture is that this picture has gaps in between the bars. But if you look at statistics data, a lot of times there'll be no gaps, okay, but it doesn't really matter. But here you have a histogram where on the bottom you again have ranges, so 40 to 45, 45 to 50, etc. And the bars are just right next to each other. Okay, and so again with this picture here, you know that there are 3,258 people, and you know that 7% of them or so make between $40,000 and $45,000 a year, and you know that 5% of them make between $65,000 and $70,000 a year. But again, you've lost the original data. Maybe of this 5%, maybe half those people make 66 and the other half make 67. You just don't know. Okay, and so that is it for section 15.1.